Hello and welcome back to another episode of Natural Number Game with Lean4. Picking up right where we left off, we're going to continue the Advanced Addition world. Level 7 is add, write, cancel, if and only if. Oops. So, theorem, add, write, cancel, if and only if, T, A, B are all natural numbers. What do we want to prove? A plus T equals B plus T if and only if A equals B. And we're going to do that in two cases. We're going to use our constructor to figure out, okay, first case we're going to do A plus T equals B plus T. So here we could do exact, add, write, cancel. And this is, okay, has type ATP, and I think we just do underscore, underscore, underscore to be like lean. You're smart, figure out what variable to put in where. And this becomes A, this becomes T, this becomes B. Great. Now what we have left, now we have the other thing to do. A equals B implies A plus T equals B plus T. Okay, A equals B. Oh, well, here you just intro equality, or intro H, I guess. And then rewrite H, raffle. Sick, that was pretty easy. Let's move on to level 8. This lemma, the lemma you're about to prove will be useful when we want to prove less than or equal to is anti-symmetric. There are some wrong paths you can take with this one. Okay. If A and B are natural numbers such that A plus B equals A, then B equals 0. Let's take a crack at this. Equal 0 of add, write, equal self, A, B being natural numbers. A plus B equals A implies B equals 0. How are we going to prove this? Okay. A plus B equals A. B equals B plus D. Okay, I have an idea how to do this. I want to turn this A into A plus 0 and then use like my add, write, cancel rule. So rewrite add 0, but like reverse. At A. Kind of. There's a step in the right direction, but I don't want both of them. I don't know why. I guess I don't know how to write just on the left side of this. I guess I can just turn 0 plus B into back to B. If I do add 0, it's going to do both of them, right? Okay. Add commutative. Now add transitive. Transitive. What's my other add? Add right commutative. No, add. I want to move the parentheses around. So reflexive? No. Add associative. Yeah, add associative. Add associative. 0 add. Nice. Okay. Now we just pretty much we can just apply our add, write, cancel. Intro H, let H prime equals add, write, cancel, if and only if, bang, 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 H. Too many things. I don't need the if and only if. What went wrong here? Is that right? Cancel not the one I want? B plus D. Oh, I want add left cancel. Add left cancel. Nice. Okay. H prime is B equals 0. Exact H prime. Nice. Okay, so I can just do exact this thing. Right? Cool. That's a pretty snazzy proof right there. Pretty proud of that one. That felt like some real math. Okay. It was pretty satisfying. No, it felt like real math. Just felt pretty satisfying to figure out what to do, what the substitutions to do where, and use these underscores in an advanced way. Now we're going to prove successor does not equal 0. Okay, so this is the last axiom of Peano arithmetic. So lemma, what's the previous one? Lemma? Sure. Or I'll just call this a theorem. Theorem 0 not equal to successor is a natural number. 0 not equal to successor of A by, that's not what we already have up here. 0 not equal, okay, no, we already have that one. Great, now we're going to prove the other one. Theorem successor not equal to 0, a natural number. Okay. Successor of A not equal to 0 by what? Apparently there's a symmetry. The symmetry tactic in lane 3 will turn any goal of the form Rxy into Ryx if R is a symmetric binary relationship, for example, equal or not zero. Well, I don't know if we have that. Symmetry. Okay, well, I don't know if there's a symmetry in lane 4. Okay, so we can prove that by first using symmetry and then that. Well, let's figure out another way to do it. Intro H. Case is H. Okay, nice. That worked. Let me look if I can figure out a way to do symmetry in lane 4. After some investigation, I was able to figure something out. So we intro H, and then there's this thing called h.sim. And so we could do let H prime equal be defined as equal dot symmetric on H. So equality symmetric, if A equals B, then B equals A. We could also do H dot symmetric instead of equal dot symmetric of H, same thing. And then here h prime is the opposite, 0 equals successor of a, where h is successor of a equals 0. Great. And now we can also let f, I think we can do this, 0 not equal successor of h prime. Oh, so this complains that doesn't know what this a thing is. So I think we could do a here like this. Then f is false and exact false. Or we could do skip this middle man, and we can even skip this middleman, so we could just do this. Nice. And then yeah, that's the successor not equal to 0. I think. Great. That solves that using the symmetric thing of equality. And then I was looking in Prelude to kind of understand how this whole thing works. Let's move on to the next level in the advanced addition world. Add left equals 0. So in Lean, a not equal to b is defined to mean a equals b implies false. This means if you see a not equal b, you can literally treat it as saying a equals b implies false. Computer scientists would say these two terms are definitionally equal. The following lemma, a plus b equals 0 implies b equals 0, will be useful in the inequality world. Let me go through, let's go through the proof because it introduces several new concepts. Oh gosh, okay, let's just try to proof on our own, and then we can see if we need these new concepts. Okay, add left equals 0, a, b are natural numbers, h is defined to be a plus b equals 0, b equals 0. By what? It's a little far off the screen, so can I move this down here? Yes. Sorry. Okay, so here we have h, a plus b. One of these also. Okay, so a plus b equals 0 implies b equals 0. Can also imply b equals a equals 0. I guess the implication is one way, so it's not direct equality, so it's fine. Oh, wait. Yeah, okay, implies b equals 0. I guess that's one way this is true. How do we prove this? I guess we can always start with an intro, or do we need? We don't even need the intro because we already have the intro kind of taken care of here. B equals 0. A plus b equals 0 implies b equals 0. I think we'll need to do a proof by contradiction somehow. Case is b with 0, sorry, successor b prime, next hypothesis, sorry, oh, we don't have induction hypothesis here. We're just doing cases, not induction. Okay, reflexive. Okay, that's easy. Now we want to prove successor of b plus 0 equals 0 implies successor of b equals 0. This kind of feels right. This kind of feels that we're back where we started. Okay. Our goal is impossible to prove. Okay. But okay, so we're getting the hint here. However, our hypothesis H is also impossible. So let's see why H is impossible by rewrite add successor at H. Okay. Successor of A plus. That is suiting, but we have successor not equal to 0. So now we can move this to a new line. Can we let F be defined to successor not equal to 0, bang H. F is false. Haha. Exact false dot elim F. Or we can get rid of this variable. Add some parentheses. You can see this is. Can we see what this is? Because it's just this is a plus b prime. A plus b prime. Cool. Now we have add left 0 solved. So because one of our hypotheses is absurd, we can prove something with it by contradiction. It's pretty sick. Now let's move on to lemma add right equals 0. A, B, defined to be natural numbers. And we want to prove A plus B equals 0 implies A equals 0. So the other way, okay. Implies, maybe implies is the wrong thing I can be used. I guess, yeah, okay, well, it doesn't, that's one of the potential possibilities. Well, this is easy, we just rewrite add commutative, and then we can exact add left equals 0. Too many. Great, that was easy. Let's move on to add 1 equals successor, level 12 of the advanced addition world. Lemma successor equal add 1 equals successor. So we already have successor of n equals n plus 1. Let's go the other way with d being a natural number. Oops, don't want that. We want d plus 1 to equal the successor of d. By, okay, do this. Apply. Nice. Wait, did that work? Okay, great. So we can apply equal dot symmetric underscore to get this, and now we can exact successor equal add 1. The right thing. Beautiful. So here we're able to have this take synthesize unification to be this whole mess. So I think I can also just copy this in, right? No. Okay, I don't know what it takes, but good thing we have equalization, unification. And that solves that proof. Final level of the advanced addition world, not equal successor self. Okay. Lemma. That's kind of cool. Lemma not equal successor self, with n being a natural number. It says that n doesn't equal successor of n. That sounds useful and interesting. How do we do this? Intro h. N equals successor of n. Well, that just seems absolutely absurd. How can we prove something false from that? Okay, I guess we could maybe rewrite or successor equals add 1 at each. What does it say? Oh, we should do it forward. And then I guess we don't need intro h just yet. Successor equals add 1. Intro h. Rewrite add 0. Add 0. I guess we also don't need intro h just yet. N. But also, now I want to do the commutative trick again. Oops. Add. Oh, it was a commutative? No, yeah, commutative. Commutative at. What was that? Add associative, not commutative. Add associative. 0 add. Okay. And now can I what's it? Left cancel, add left cancel. So left thing is both n. Okay, that didn't work. Okay, let's intro h. We should apply left cancel. Do we apply it? No, we write it. Rewrite that h. What happened here? Let f be defined. Oh. Okay, I apply, but don't intro h. Okay, let's just go back to what we had. Okay, so f is 0 equals 1. Our goal is false. Well, 0 does not equal 1. Do we have that in addition world? No, in where do we have that? Where is our proof that 0 does not equal 1? Where do we even have 0 and 1 in addition world? Tutorial world, maybe? Add 0, add 1. 1. No, not here. Maybe in Lemma? No. Okay, I feel like we're close, so we've pretty much reduced it to how do I prove that 0 doesn't equal 1? Oh, we can turn 1 into successor of 0. Yes, and then we also have 0 not equal successor. Okay. We have progress. Okay. Can we rewrite f at h? Does this work? Do this. Got some like weird name collision. Oh, okay. Now our goal is what did this do? Plus 1 equals n plus 1. Huh? What the heck? How do we go from here to here? Oh, well, using 0 equals 1, we have this. That's a little silly. Let's not do that. Let's instead turn 0 into, or 1 into successor of 0, which I think we have. 1 equals successor of 0. Rewrite 1 equals successor of 0. Add f. Nice. Okay. Now we can use this at f. Fill in the right variables. Okay, no, that's not quite right. Let f prime be defined as 0. F. False. Okay. Can you do this? Okay, fine. That's fine. Well, we can just do exact of this. Exact this. Hell yeah. Okay. Because this whole thing is just false. Because using this thing and plugging in 0, we have something that's false. And that proves that that n is not equal to successor of n. And that solves the advanced addition world. Thank you so much for watching and sticking around. Yeah, I hope you enjoy the next episode where we tackle the advanced multiplication world. That's next, and then after that we have the inequality world, and then we're done with a natural number game. Thank you so much for watching. Leave a like, leave a comment, and check out the next video. Bye.